So the objective for this lesson is to graph exponential growth and decay, tomorrow decay functions. Okay, probably going to be wanting to take notes if you're, this is your set of notes. Obviously, I'm not passing out notes this semester, so. A little bit of vocab before we get started. The word asymptote, which, yes, sounds pretty funny. Okay. We need to understand what an asymptote is. Okay, it is a line that the graph of a function approaches but never crosses. So exponential functions are our first functions that have what we call an asymptote. There's going to be a line, and I'll highlight it as we graph these what that line is, but there's going to be a line on the graph that the function will forever get closer and closer and closer to. It's like that annoying little brother who's like, I'm not touching you, I'm not touching you, as he gets closer and closer. Okay, well, asymptotes are actually never touched. You know, eventually your brother actually probably touches you and whatever, but this is, it just gets closer and closer forever. So let's graph an exponential growth functions here. So these are growth functions. Tomorrow we're going to do decay functions. So the first example, it's going to be a simple one. This is something that you would have been expected to graph in Algebra 1. So 3 to the power of x. So here, guys, notice the variable. The variable is part of, well, in this problem, it's the entire exponent, but it is part of the exponent. That's what makes it an exponential function. So when we graphed these in Algebra 1, we always just graphed the domain of -2, -1, 0, 1, and 2. Okay? And so what that looked like, we plugged these into the function. So this would be 3 to the -2nd power. Guys, 3 to the -2nd, remember your properties of exponents. You get a no negative exponent, so you got to move that to the denominator. Guys, this is just 1 over 3 squared, which is 1/9, 1 over 9. And so on our graph, what our graph would look like here would be, so we have our x-axis, our f of x-axis. We've got the point -2 and 1/9. Guys, 1/9, very hard to graph accurately. Guys, it's just above 0. If you think of 1/9 as a decimal, it's 0.11 repeating. So that's very close to 0. Can you guys all see the dot there that I put just above the x-axis? And so if we evaluated 3 to the -1st, guys, properties of exponents, that's just 1 over 3, which is 0.3 repeating, 1/3. So again, that's also difficult to graph. It's a little further from 0 than 1/9. So maybe try to make it a little bit above it. Guys, honestly, sometimes I make mine just straight across. It's tough to graph those first couple points. So here we're substituting 0 for x. So 3 to the power of 0, guys, anything to the power of 0 is just 1. So this is the ordered pair 0, 1, which is right there on our f of x-axis, or y-axis. Plugging in 1, 3 to the power of 1 is 3. So at 1, we're up to 3. And then plugging in 2, 3 squared is 9. So at 2, we're up to 3, 4, 5, 6, 7, draw your graph, guys, this left part of the graph is going to be very, very flat. So almost a straight line through there. I mean, it's going to end up having to be pretty much a straight line. And then it obviously starts growing very quickly, and this is what we call exponential growth. That graph is exponential growth. In fact, you might have heard a lot of talk about, when the virus first started spreading, we're trying to flatten the curve. Well, that's because the spread of a virus is exponential, okay? That's why we're trying to do things like social distance so we can break the curve, okay? The way it works, if someone gave it to Nathan and 3 people are sitting next to him, and he gave it to all 3 of those, and then they gave it to 3, and they gave it to 3, every person out, it increases by a factor of 3. It grows exponentially. So if it started here at 0, or, why did that text box go in there? Undo that. Sorry, guys. We started here with 1 person having it. Well, he gave it to 3, then those 3 gave it to 3, so now we're up to 9. Those 9 all give it to 3, so we're up to 27, and it just grows very fast. So that's exponential growth. So asymptote, I said we talk about this. This is a very good example to talk about an asymptote on here. Okay, if you guys notice at 0, okay, right along the x-axis, I'm going to use another color here. This function is going to get closer and closer to 0, but never actually get there. As you go to the left here, so if I plugged in other points to the left, like if I said x was -5, and I substituted that in, I would have 3 to the -5th, guys. That is 1 over 3 to the power of 5. I have no idea what that is off the top of my head, so I'm just going to plug it into my calculator. That's 0.0041, blah, blah, blah. I went 3 to the -10th. That's 1 over 3 to the 10th, which is an even smaller number. That's 0.000017, blah, blah, blah. Okay? The further you go left, the closer the function gets to 0. But if you went all the way out to -10 billion or -100 billion, that's still never going to actually be 0. It's going to just get closer and closer to the asymptote, closer and closer to the x-axis, without ever touching it or crossing it. Okay, so that is what an asymptote is. And this is exponential functions are our first really good look at them. Okay. Questions on this first example? I think we got somebody joining. Oh, you got booted, didn't you? All right. So this is the simplest form. Guys, as we get into way more complex exponential functions, which we will, you're going to need a scientific calculator to simplify them. This one was easy enough because I know what 3 squared is. I know what 3 to the 1st is. But as we get into more difficult problems, you're gonna want the calculator. Okay. So let's do one more example here of a growth function. Let's do a simple growth function without any transformations. Let's go f of x equals 4 to the power of x. And again, when there's no transformations, we're just plugging in -2, -1, 0, 1, and 2. This is probably one most of us can do mental math on. We know what 4 squared is, right? We know it's, what, 16? So this is 1 over 4 squared, or 1/16. So -2, we're at 1/16. which is, again, just really close to 0. We plug in -1, we're at 1 over 4, which is 0.25. So maybe try to go a little higher there. Anything to the power of 0 is 1. 4 to the first is 4. And 4 squared is 16. So 4, 5, 6, 7, 8, 9, 10, 11, 12. So in fact, this one, I haven't made my graph tall enough. I would be, just estimate somewhere up here. I didn't get up to 16 on my graph. I didn't make it long enough, but you're getting the idea here. Okay. One really important note, when you connect the dots, when you graph, make sure you don't cross the asymptote. Okay, so what do I mean there? If I was graphing this, what I do not want to see is you guys to have like a rough sketch of this, which that's what these are, guys, a lot of these points, and then I don't want you guys to go like this, okay, and just sloppy cross the asymptote. Make it a flat line, make it not cross the asymptote like we do here, okay? Needs to look good and realistic. Everybody understand what I'm saying here? Okay. Questions so far? Okay, let's make another page here. Now we're going to talk about transformations, guys. Little note, these are the same type of shifts as radical functions. So, guys, we looked at A, we looked at H, we looked at K when we looked at radical functions. We're doing the same thing here for our transformations of exponentials. So if you're familiar with the radical functions, which some of you guys were paying attention during that lesson, then this should look familiar. If you weren't, well, maybe this will help you with the radical function. So, guys, if this is the standard form, this is the normal format, a times b to the power of x minus h plus k, okay, then h is going to be your horizontal movements. That's going to change the x values you plug in. Highlight this, do something about this. This is going to change your x values. That's going to, instead of plugging in -2 to 2, if we have an h value, a shift left or right, we have to change the x values we plug in. I'll show you an example of that, like in a problem, a couple problems, but you have to understand that h is going to change the x values you're plugging in. Okay. So how does it change it? How does h change the x values? Okay, the function moves h units right, so to the right, if h is greater than 0. So if we have x minus 2, x minus 3, x minus 4, that's moving us h units right. So example, we have x, 3x minus 2. If we had this function, this is a shift 2 units right. Okay? It's going to move h units left if h is less than 0. So what does that look like? Well, say we had f of x equals 3 to the x plus 2. Okay? Because the standard form is a minus h, this means that h is negative 2 here. So we shift left 2 units in that example. That would be the shift. X plus 2? Okay. Gotcha. So you guys see the difference in what h does there and how it's going to shift our functions, right? Okay. Shift with an H. Yep, not Swift. Shift. Okay. So K, if H moves you horizontally, K moves you vertical. Okay, so that changes your f of x. That changes your range values, which isn't hugely important, but we still need to note how that changes things. So it moves it K. I guess I'm kind of color coding this, so let me do that as well. So that's going to move this K units up if K is greater than 0. If K is positive, it moves it K units up. So an example of this would be f of x equals 3 to the power of x. So that K, it's outside of the exponent, guys. It's not as part of the exponent. So here it's positive. So this is a shift up 2 units. That's a shift up 2 units. Okay? It's going to move us K units down if K is less than 0. So if we had 3 to the power of x minus 2, now this is K is less than 0, so this is a shift down 2 units. A lot of writing. Okay. The last letter that's going to change anything is A, and that changes orientation, meaning if it goes up or down, and shape. So A changes orientation and shape. Guys, A is just what's multiplying before our base. And we'll see an example of that here in just a few minutes. So a couple of notes about A. If A is less than 0, the graph reflects about the x-axis. Okay? Someone else joining us here. Yep. And so what that would look like, guys, instead of the function going up like that, this function would go below the x-axis. Okay? So that's what a reflection about the x-axis is. Goes down instead of up. If the absolute value of A is greater than 1, the graph is stretched. How am I spelling stretched? How do you spell stretch? Switch my TNC. stretched vertically. If A is the absolute value of A, it's greater than 0 and less than 1, meaning it's a fraction, graph is compressed vertically. Okay. So the best way to address these, obviously we have these vertical and horizontal shifts that are pretty clear. A is a little more iffy probably. So let's just look at some examples then. Pull up. I think I got 2 more examples for us here. So the first one is a pretty simple example. It's the function f of x equals 2 to the power of x plus 1. Okay? Guys, that plus 1, is that an h? Is it a k? Is it a? What is it? Is it part of the exponent? It's not part of the exponent, so that means it is k. Okay? And it's a positive 1. It's a plus 1. So that means it's a shift up 1 unit, sorry. So this is k equals 1. That is a shift up 1 unit. Okay? This example, there's no h, so I'm going to make a note of this. No h, so x values the same. We're going to plug in the same x values. -2, -1, 0, 1, and 2. Okay? When these x values get to be, or when we start to have h values, we're not going to always plug in -2 to 2. So substituting in -2, this is going to be 2 to the -2 plus 1. On your calculators, guys, because we're going to need to use scientific calculators, you might not need to use them on this one. You could maybe do some mental math, but you're going to do 2. Then you're going to have to hit that caret button. Kind of looks like a caret, like that. You're going to put parentheses, -2, close your parentheses, and then do the plus 1. If you do not use those parentheses, it will think the plus 1 is part of the exponent. This plus 1 is not part of the exponent. You have to use the parentheses. If you don't use parentheses, it will not work. You will get the wrong answer. Does everybody understand that? Use parentheses. Okay, when you plug this in, what do you get here? You get 2 to the -2, and then plus 1, 1.25. This is 1.25. Okay, when you plug in -1, I'm going to write it again how I would write it in my calculator. We're going to get 1.5. Plug in 0, you get 2 to the power of 0 plus 1. Which is 2. This one you could probably do mental math. 2 to the power of 1 is just 2 plus 1. So that's going to be 3. You can plug it in if you'd like. 2 to the power of 2 is 4. 4 plus 1 is 5. Okay, so maybe you can still do some mental math on some of these. Most of them probably going to need calculators for. Sketching a graph of the function. At negative 2, we're at 1.25, so that is slightly above 1. At negative 1, we were at 1.5, so between 1 and 2. At 0, we were at positive 2. At 1, we were at 3. At 2, we were at 5. Okay? Who has any idea what the asymptote would be here? Not that I'm going to always ask, but just so that we can kind of see how this changes our asymptote. These first few examples, guys, the asymptote was at f of x equals 0 or y equals 0. Guys, if we shift the graph up 1, then the asymptote is going to be at 1. Okay, at that line y equals 1, which would be, guys, right there, that horizontal line. Okay, everything got shifted up 1. That was because we shifted up 1 unit. In the standard problems, Corey, the asymptote was right here along 0, right? That's when we didn't do any changes to our function rules. Okay, so if we shift everything up 1, instead of at 0, it's going to be at positive 1 here. And again, I'm not going to always ask where the asymptote is. That's something we need to start considering, because as we get to rational functions, we're going to have asymptotes everywhere, and it's good to have an understanding of what an asymptote is. Questions on this example? Mason? The function, you're kind of confusing it. So in these first two problems, the asymptote was the x-axis. It's the y equals 0. The function was never going to touch the x-axis. In this example, it can, yeah, if we shifted the function down, it could cross the x-axis. This first example, in fact, I think our next, now, there's one on our homework where it has a shift down. So just imagine the picture. I mean, I'll just draw a quick example of it. If we had something that shifted down 2 units, so 2x minus 2, say this shifted down 2 units. Then instead of, I'm going to graph the original here in blue, instead of it being right there, if we shift it down 2 units, then it's going to be down, everything's just going to be 2 units lower. So guess what? Yeah, that crosses the x-axis. Okay. The function will never cross the asymptote. Don't consider it the x-axis. Wherever the asymptote is, it's not going to cross it. So the next example, definitely the most complex so far. I'll add a new page here. F of x equals negative 1/2. That's going to be our a value, times 5 to the power of x minus 2. Okay. We said it had an a value. Here, a is negative 1/2. We'll list what that's going to do to it here in a minute. This minus 2 up here, is that an h or a k? That's an h. And that is an h equals, remember, it's always x minus h. So here h is positive 2. Okay, kind of backwards for the h. Okay, so if a equals negative 1/2, how does that change my function? Well, so a is less than 0, it reflects across the x-axis. Okay? And because a is a fraction, because a is between 0 and 1, the absolute value of it, it is compressed. Vertically. Okay, so compressed. Think about taking a marshmallow between your hands and squeezing it. It gets wider, faster, not quite as tall. Okay? Compressed vertically. If h is 2, h is positive 2. So if h is positive, greater than 0, it shifts us right, however many units of h. So this is a shift right 2 units. Okay? That shift right 2 units is going to change the x values that we plug in. Instead of plugging in -2, -1, 0, 1, and 2, add 2 to all of them. So just go start at 0, 1, 2, 3, and 4. Guys, we can think of it as adding 2 by offsetting the subtraction of 2 that's going on in the exponent there. So h changed what x values we're actually going to plug into the function. At this point, guys, my mental math is going to fail me. So I'm going to stick to the calculator here. Let me write out exactly how I'm going to plug this in. Yep. It would have shifted us left 2. So instead of -2, subtract 2 more. I'd plug in -4, -3, -1. Yeah. Like what you're really thinking about is the x-axis. So if you're shifting right 2 on the x-axis, all your x values are going to increase 2. If you're shifting left 2, all your x values are going to decrease 2. Okay. So how I would plug this in on the calculator, guys, you're going to go -1. I'm writing out how I would just so you guys are all clear. -1 divided by 2 times 5. You got to go to that caret button. We got 0 minus 2 in the exponent because we're substituting it for x. You plug all that in. I don't know what you get. Like I said, the mental math is going to fail me at this point. -1 divided by 2 times 5 to the power of 0 minus 2. This is -0.02. Let's plug in 1. -1 divided by 2. 5 to the power of 1 minus 2. -0.1. Plug in 2. You're going to get -0.5. Plug in 3. You're going to get -2.5. Plug in 4. -12.5. Guys, the graph of this is a lot different. we reflect it across the x-axis. So that means I'm going to go down, okay? The graph shape is a lot different. I'm going to be down in that third quadrant a lot more. When I plugged in 0, we got negative 0.02, so that's still really close to 0. That's like right, really close to the origin, guys. Just below it. 1, 2, 3, 4, 5. I probably need to make my x-axis a little, or my f of x-axis a little closer together. So bear with me here. Negative 1, 2, 3, 4, 5, 6, 10, 11, 12. We're going to go down past negative 12. So when we plugged in 1, we got negative 0.1, which is still really close to 0. We plugged in 2, we got negative 1/2. We plug in 3, we got negative 2.5. We plugged in 4, we got all the way to negative 12.5, which is way down here. So that's the bell. Okay, that was our last example. Have a wonderful afternoon. Get your Canvas assignment done. That was a proper Algebra 2 class.